So in this video, we're going to take a look at how to use Bricklayer to construct X-shaped artifacts in the XZ plane. And rather than looking at the specifics and the nitty-gritty details of the code, we're going to take a mathematical look at this problem, so from a mathematical perspective. Now, before we get started, I'd like to make a couple of remarks. First, I'd like to point out that we're going to take a look at a sort of a sequence of problems and their solutions, and the nature of this sequence that we're going to look at has the property that earlier problems, the solutions to those problems can contribute to the solutions of more complex problems that occur later. Now, related to that is the idea that this approach to constructing these X-shaped artifacts ultimately is decompositional in nature, or compositional depending on what your starting point is. Validation of your mathematical ideas is essentially a continuous process, and it's visual based. So you have a Bricklayer program, you try a particular formula, you run the program to see if what you are picturing is really what's happening, and then you can kind of make adjustments and clarify your understanding as needed. And then last but not least, parameterization plays a key role in taking a solution to a simpler problem and generalizing it to a richer kind of a problem. All right, so what we're concerned with is a grid that exists in the XZ plane, and this grid has a number of cells in it, and it's square, and we would like to occupy some of these cells with bricks, Lego bricks having particular colors. And another thing I'd like to point out with is that the coordinates of these cells are described by integer values. So an integer x value, an integer z value we have, so it's a discrete space. There's no real numbers going on here. All right, so a little bit of background before we get started. In Bricklayer, you can write conditional expressions. And so a conditional expression has an example of one is shown right here, and it basically reads as follows. If some property is true, if a predicate is true for a particular set of inputs, then I can say color the cell that you're applying this predicate to black, otherwise leave it empty. And I can generalize this idea with multiple predicates, so I can have multicolored an artifact where cells are colored with different colors depending on what their properties are. In this case, properties of their coordinates. So if property 1 is true, then color the cell red. Otherwise, if property 2 is true, then color the cell white. And otherwise, if property 3 is true, then color it blue, and otherwise leave it empty. So here's an example of a diagonal line. So it's an artifact that consists just of a diagonal line. And the question now is, what is the property that coordinates need to have in order to be colored black? And the property here is that whenever the x value of the coordinate equals the z value of the coordinate, then you color the cell black, and otherwise you leave it alone. And so then the code, the conditional expression that would correspond to this is, if p of xz is true, then black, else empty. So that's the idea. Okay, so now let's try having the line go in the other direction. And again, we're dealing with a square grid here, and we would like the diagonal to run, the black line to run across the major diagonal from the upper left to the lower right. And so here then, the problem gets a little bit more complex. It is helpful to know the formula for a line that can be applied to solve this, to determine what the property is that needs to be satisfied in order to be colored black. However, you can also reason this out directly. So the question then here is, what is the predicate? And it is worth noting that whatever that predicate is, it does depend on n. So it's parameterized ultimately in some way on that as well. Okay, so now once we have the diagonal lines going in both directions, we can compose them. And so we have a predicate that describes one diagonal, a predicate that describes the other diagonal, and we have this, the size of this square, the width. And so I could write a conditional expression as follows. If property 1 is true, then color the cell black. Else, if property 2 is true, then color the cell black also. Else, leave it empty. Now, it is important to notice that n plays, there's an additional constraint that's placed on n in order to make the lines cross at a single cell. So what is that property? That's also needed if you want to basically create x's of arbitrary size that look like this. All right, new variation on the problem. So we'll back up again to doing just a diagonal. And here, this time we want, rather than filling in a single square, we'd like sort of our squares to be bigger. So this is a 3 by 3 square here. In general, it would be a k by k square. And so a couple of things to notice now is that the width of the grid depends on k. And of course, we know that the predicate also depends, well, in this case may not depend. Yeah, it actually does depend on n, which depends on k. And so the problem has just gotten a little bit more complex. And our next step then is, once we've figured that out, is to create our x, so to have the diagonal lines going in both directions. And again, so there's an additional set of constraints that come, that are placed on n as a result of this. So the trick is, or the question now is, find out what these properties are. And now, new variation of the problem. Suppose that you decided that you got hired at Microsoft and they wanted you to create one of these x's, these x-shaped artifacts, where when the diagonals cross, they don't cross on a particular square, but they cross sort of adjacent to each other. And that adjacent corner here, what results in this intersection is the Microsoft logo, or the color scheme of the Microsoft logo. And so again, so the way one would do this, I'm just going to point out a couple of things, right? That the one diagonal, the cells alternate between blue and green, and the other diagonal, the cells alternate between red and yellow. And so we can take this more complex conditional expression that I had mentioned at the beginning of this talk as an example, and adapt this kind of a structure to describing multicolored artifacts. So now the question here is, adapt these ideas to be able to construct something like this.